Wasabi, you guys. Silver here, and we're gonna do some MIT integration bee problems from 2010. All right, so let me just do something real quick. All right, first integral is a definite integral that I just don't like definite integrals in general. It's just me. There you go. It just goes on and on forever. dx. Okay. So how would you speed and integrate this? Alright, so we need to change that function. As you can see, it's an infinite function. So I'm going to let that function equal w. Okay. And we're going to go ahead, let's see, this is 1 plus x. And then, of course, this is equal to the inside of itself, right? So this is w inside there. Okay. Now we go ahead, solve for w. Yeah, we pretty much solve for w. Let's see, square both sides. Minus xw minus 1 equals 0. Use the quadratic formula. So w is equal to negative b, in this case it's positive, plus or minus square root of b squared minus 4ac, so that's plus 4, all over 2. And that is the integral you will be solving, okay? Because this is equal to this, okay? And that's also why I hate definite integrals. Okay, so now we got that. I'm going to go ahead and integrate. This part is easy. This we might have to do trig sub. So we're going to go ahead. That's good. So we know this part here, but because we're going 0 to 1, we're going to be using positive. Okay. So x over 2, the integral of x over 2, that's like x squared over 4. Okay. Plus the integral from 1 to 2, the square root x squared plus 4 divided by 2. Okay. Now, at this point, this is trig sub. Okay, we're going to let x is equal to 2 tan theta. Okay, in case you want to reference yourself, you could also do dx 2 secant square theta. You could do that as well. Okay, just to reference yourself. But I don't usually write dx. When you integrate a lot, you'll get used to how this works. So we know for sure this here when we plug into tan theta, we're gonna get like 2, and then end up with secant theta. And then, oh, this 2 is here. This cancels. And we have a nasty integral, as you can see. Oh, well, we have that 2 secant theta. I mean, 2 secant squared theta. So 2 is still there. I'm sorry, not 2. A half. Because wait, dx. No, that is right. Sorry. 2. Okay. Secant cube d theta, that is an integral. If you are a speed integrator like me, that is an integral that you must memorize. So in this case, this is 2 secant cube. This is secant theta tan theta as an answer. So now that we got that, you plug it back into the X world. I don't like doing the Pythagoras method where you draw a triangle and then do whatever. I don't like that. So I'm just gonna write it trigonometrically. That's right. This is a definite integral. God dang it. I really hate definite integrals. Okay, so this is plus secant secant of inverse tangent of x over 2 times tan theta is x over 2. Okay, because tan theta is x over 2 plus, oh dear God, this thing. Well, so if this is a definite integral, what I would do is I would be like, okay, let's let, I should have told you guys this earlier, but let this equal a. Okay, so I'll do a plus x over 2. Okay. Practice doing this though. Do not just watch this video and then apply this during the competition. Don't do that. You're gonna have to practice this a lot, especially when you end up with trig like this. You can just write a, but you have to know what a is. Never forget about it. Okay. All right. So when we plug in 1, when a is 1, that's what? Well, if a, let's see, the inverse tangent of a half, that is, what is it? What is that? Inverse tangent of a half? 26.57 degrees. So it's not part of the unit circle. Okay. Now you know why. So this is also another reason why I hate definite integrals. Okay. So you just write it as, so there is nothing. It's not even part of the unit circle. So that's a. A is a half secant inverse tangent of half. Okay. And so we end up with 1, this is 1/4, plus secant. I don't have a huge whiteboard, so I'm just gonna write like that. Divided by 2, plus that again. Why? And then a half. Let's see, this is. I really don't want to write this again, but I gotta have to. And now I don't have any more room. And then if I plug in 0, that's 0. This is 0. Secant 0. What's secant 0? Oh no, don't tell me. This better not be improper. What's secant 0? Oh no, wait. I'm sorry, it's not improper. That's 1. So that's 1. Okay. So we have minus 1. Minus 1, it's negative 3/4. As you can see, changed it. Negative 3/4 minus 1. Minus, let's see, 0. ln of 0. I'm sorry, no, 1. That is 0. Okay, so this should be our answer. Okay, because if I plug in 0 here, this is just ln of 1, which is 0. This is 0. So they're both 0. You only get this, which is equals to 1. Wait a minute. 1, 1 1/2. Shoot. 1/4 minus a half. What's 1/4 minus a half? 1/4 minus a half. Negative 1/4? Okay, that's our answer. Oh God. You know what? Maybe I'm just gonna show you the indefinite solution, and then you can do the definite integrals yourself. Because some of these are definite integrals, and I hate definite integrals because I'm not a mathematician. Okay. Next integral. Okay. Holy macro. What do we do? What on earth do you do? Well, just staring at this, this really does scare me. You know, let's see. Well, the first thing I want to do is I want to hope that these will become cosine plus cosine something. Okay, so here's what I mean. So there's a trick to where when you have a sine or cosine or sine cosine, there's a trig identity. In this case, I forgot, but I have a backup memory for this. So let's see, cosine, sine. That's the only way. Cosine, sine. And then we have cosine, sine. Okay. In order for me to have sine, okay. Like this. In order for me to have cosine, sine, this has to be minus. Okay. In order for me to have 2 sine, which is cosine, sine. So this is c with a minus plus c the plus. You see where I'm going to. So if you know your laws like cosine a plus b, cosine a minus b, this is cosine a minus b minus, that's that minus cosine, this is cosine a plus b, okay, which is why I put it plus right there, okay? And so doing that, this goes here, okay? So that's my memory backup. That's my memory plan. If I forget the identity, I do that, okay? So now that I know that, this is a half. So yes, that's cool. Yes, that's exactly what I want. I want 2 cosines, because now what I have is, well, cosine. So I need a subtraction of this. It doesn't matter which way. 2 minus 1. It's x cosine. That's 3x because 2x plus x is 3x, and that's all multiplied by 3x. This is easy. This is going to be a pain. Okay. So a half of cosine x of sine 3x. Okay, and then I have minus a half of sine. What I could actually do is I could go do half 2, that's going to be sine 6x. Okay, let's see if that does that right. 2, yeah, should be. Okay, now we have to deal with this moho here. So let me just, okay, because I forgot the memory for this. So this is, let's see, cosine, sine, cosine, cosine, sine, sine, cosine, sine, sine, cosine, cosine, sine. In order to have that, I don't think it matters. So it's just sine, sine. Okay, so this is just 1/4 of, let's see, plus, am I adding? Yes, I'm adding. So this is sine of, let's see, 3 plus 1, 4x, plus, I'm adding, so that this cancels out. So this is subtracting. Yeah, because I'm adding whatever this is. This is sine 3 minus 1 is 2. Or you could do x minus 3 in absolute, because it doesn't matter which way. Okay, and then the integral of 1/4, which is sine 6x. Wow, okay, I could actually combine them together, really. Okay, do not do integration by parts, because that's nasty, unless you're very fast at it, and then, I mean, you know what, go ahead. Go for it. Okay. That looks like a parentheses, that's a 6. Okay. So 1/4, all that multiplied by 1/4. Oh god, and then so now we have, are these all negatives? I think so. Well, in that case, I guess we're going to start right here, because the integral of sine of something is cosine. So this is cosine 6x over 6, okay, minus cosine 4x over 4, minus cosine of 2x over 2, plus c. Is that correct? It does. It's not gonna. It likes to simplify, so it did landed when I did the derivative of this. It landed to these integrals, so that's very good. At this point, I really don't know, because this thing is. I hate math computers because they simplify too much and they never go on multiple answers. So I really don't know. Yeah, I'm just gonna, you know, if you do see any mistakes that I did, please let me know in the comments. Because I don't know what went wrong. Okay. I'm not quite sure about this. I can reform this. And so now this is ln of x plus 1 minus x ln of x. Okay, so integration by parts. Probably the only way we could do. Yeah, because I don't know otherwise. I don't know anything else otherwise. So when we do ln, let me erase that portion because we're pretty much integrating this now. Ln of x, ln of x plus 1 is negative x plus 1. This is x half of x squared. As you can see, I don't like this already. I really don't like this integral already. I'm going to imply that negative ln of x and we get 1 over x. This x becomes half of x squared. Okay, not bad. So we do have, so first of all, I'm going to put my answers up here. X plus 1 minus half of x squared ln of x. Okay. And now we're left with two integrals. Okay. I don't have a big whiteboard, so please bear with me. Okay. We have the integral half. So it's a negative integral. Okay, I have the half x squared x plus 1, and then the other side we have plus half of x squared over x. Okay, so that's the two integrals we have right so far, all from integration by parts. This is x. This is just becomes x, and so we have plus 1/4 x squared. So we're done with that. Okay. Here, so now what? Some of you would do a lot of people would do polynomial division. I really don't like that. So what I'm gonna do is instead I'm gonna do, see, I already know x plus 1 minus negative, well, so here I did minus 1 x plus 1, which is like negative 1, so it's like 1. Okay, so this is just x minus 1, obviously, because that's exactly what I was aiming for. I needed to do this so that I know what I have left, so that I could be like, oh, okay, x minus 1 plus 1 over x plus 1, and then I could comfortably integrate without having to worry and check with my small brain. So and I would add that into the solution, in which I'm too lazy to write because okay, let ln the u equals ln of x. Okay, so that e to the u, oh my god, e to the u is equal to x, and e to the u du is equal to dx. Okay, so you should end up with like sine square, yeah, sine square of u e to the u du. Okay. Alright, now you're asking, okay, Silver, you literally just gave us a very ugly integral. Well, MIT always gives you ugly stuff in the first place. So, what can I say? Sine square u and e to the u du. Well, what can we do? What can we do? Do. What can we do? Do. So, what you can do is you could go like this. You can make this to half minus half of cosine 2x. Sorry, 2u. E to the u. Okay. The only problem is that this is a 2u, not a cosine u. If this was a cosine u, it would be easier because this is an integral to memorize, and so has the sine as well. But this is a cosine 2u, so you might have to integrate by parts hand. This you could do on your own. I'll do this part, e to the u. So doing the derivative is much easier. Okay, cosine, I just leave the constant out. Well, actually, you can bring the constant in. I'll take the negative to here to the cosine. God dang it, marker. Then half e to the u. This just goes like that. And then we have, let's see, deriving this, we get positive s. See. Okay, that's it. Go like that. I'm sorry. This is cosine 2u. So 2s negative 4. Okay. This, you should end up with whatever that integral is. You have I, this is I, so you pretty much have I, this is already negative. This is negative, right? Yeah. So you have minus 4i equals negative I, right? So either you just do divide, I'm sorry, subtract 4, so this is negative 3, and then you multiply your entire answer with negative 1/3. Oh, that's such an ugly integral. And then you also have to plug in u back. I don't know how MIT does that in super fast. They use real analysis, I just use algebra. Okay. I think it was the last integral. Oh god, I'm so glad I'm not doing the definite integrals ones. Do you know how horrible it would be to just do those kind of definite integrals? So horrible, so horrible. Okay, so that's what it shows. Okay. Well, it shows that, but I just turn it into square roots. Just because it's easier and faster for me to write. I'm checking, making sure that's all the 2010 integrals. And it seems like that is all of the 2010 integrals. Seems like it, yeah. Okay. Well. Oh god. Alright, so this would be x squared. So I'm just going to do this quadratically. X squared minus, let's see, that's what? 2x, oh, positive, minus 2? Is that correct? Did I do that right? 2x, x, yeah, I think so. Okay. And then you just complete the square and then do the trig sub here. This is x, let's see, 3 halves. Oh boy. What are the name is this? Halves? 3 halves? And so you have to square that. 3 halves. Oh, why? 9/4. Okay. Negative 2 equals 9/4 plus what? So, oh god, why? This is 8/4. X is equal to negative 17/4. What is this? Why? That's nasty, bro. I don't want to do this. Okay, well. Oh my god. 17. God. That's so horrible. It's horrid. That literally is horrid. Look at this. Well, I mean, I guess that's a constant, but like, that's just nasty. And then this is just x plus 3 halves. Square minus that. And then you're gonna have to do let secant. That's so disgusting. 17/4 secant 2. We're gonna let that equals let this equal x plus 3 halves. Trig sub, and then good luck. Okay. All right. That's that for that integral. Yeah, that's it. That's all the 2010 ugly integrals from MIT. Okay, so that's it. Just want to show those techniques, so hopefully you guys find helpful for those. Thank you guys so much for watching, and I'll see you guys in the next video.